Okay, so we'll get started here. And all right, so we'll start covering Markov chains. Okay, so I think this is exciting. I don't know, I'm excited, but I get excited about this stuff. Anyway, all right. So so in the context of well, okay. So just before I get into Markov chains, I think maybe just a little bit of taking a step back and looking at the big picture could be helpful. So in the context of Bayesian stats, we want to find the expected value of a function, right? So this is a common thing that we want to find. We want to find, h of x and maybe the expected value of h of x, where x comes from some distribution f, right? And that's going to be something that pops up a lot in Bayesian stats, where you do your analysis and you get a posterior distribution for x, and depending on the distribution, the integral, solving this integral, so the expected value is going to be kind of the integral of h of x times f of x, and solving that integral directly could end up being difficult. And so we can what we can do is we can estimate this via Monte Carlo estimation, right? We just generate a whole bunch of random values of x, we plug that into h of x, and then we take the sample mean, and we've done that a few times in our homework. And so Monte Carlo estimation, though, it depends on our ability to generate random values, a sample of random values of x. Okay, so that's kind of the that's a major thing that we need to do for Monte Carlo integration, or estimation. And so we talked about ways of generating random variables or random values. We've got inverse CDF, we've got convolutions, we've got rejection sampling. And so these are all ways to generate random values of x. And an inverse CDF is effective and efficient, but it requires that we find the CDF and the inverse of the CDF, which can be difficult. Rejection sampling doesn't require that you find the inverse CDF, but it can end up being inefficient. And so I've got a few slides to kind of show you how inefficient it can end up becoming. So here's an example where rejection sampling is not going to do a good job here. Okay, so let's say you want to generate values from the t distribution, right? And so we've already seen rejection sampling applied to the normal distribution. And we say, well, you know what? Rejection sampling worked well for the normal distribution. We folded it in half, or at least generating from the folded normal distribution, we can fold it in half, and then you generate values from the exponential distribution, and then use rejection sampling. And then so we might say, well, the t distribution is similar to the normal distribution, so we'll try this out, okay? And we'll try a similar approach, but we'll see we're going to run into some problems. Okay, so if you look at the PDF of the t distribution, this is the PDF of the t distribution, and what I'm going to do is I'm going to fold it in half. So my folded t distribution is going to be twice as tall. Okay, so I've got, this is my f of x. It's twice as tall as my PDF of the t distribution with 3 degrees of freedom. Okay, so this is my the PDF for 3 degrees of freedom. And we're going to try proposing values from the exponential distribution. So I'm going to propose values from e to the negative x. Okay. Now, both of these have the same support, that is going from 0 to positive infinity. So our design should work. But one of the issues is that when you do rejection sampling, you need to find some value m, so that m times g of x is going to be greater than f of x for all x, right? So you've got m times g of x, and if you look at your homework, sometimes figuring out m can be a difficult thing to do. Okay, And in this case, if we search for m, where we're going to set m equal to the max of f of x divided by g of x, we run into a problem. So if you look at f of x, okay, it's basically 2 times, we got a constant times a constant divided by, and then this is, you've got a polynomial down here, and we've got 3 plus x squared quantity squared. So this is going to be on the order of x to the 4th power, okay? So f of x decays on the order of x to the 4th power. You got x to the 4th in the denominator, so f of x is going to kind of shrink. As x gets larger, it shrinks on the order of x to the 4th, okay? If you look at the exponential distribution, however, you've got g of x is equal to e to the negative x, okay? So this decays a lot faster, right? So the tail of g to the x, tail of g of x decays on the order of e to the x, okay? It's e to the negative x, so that's 1 over e to the x. That decays way faster, okay? And so we would say f of x is heavy-tailed, okay? Compared to e to the x, it is much heavier-tailed. And so what this means is that no matter how big of an m you choose, eventually as x gets larger and larger, what's going to happen is that m times g of x is going to end up being less than f of x. And so I've got a few slides to kind of illustrate this, right? So this is what it looks like if you plot f of x and g of x just directly. It looks like this, and when you plot this, it feels like, oh yeah, rejection sampling can work well. All I have to do is just scale up g of x a little bit, m times g of x. We scale that up, and then we'll draw values from g of x, and anywhere where it's greater than the red line, we'll reject it, and when it's below, we'll accept it, okay? And so, if I just say, well, let's choose m equal to 1.5, it looks like it could work, right? So if you recall, this is what we did for the normal distribution. We started off with this, okay? G of x is the exponential, and f of x is the normal, folded normal. And we just said, okay, all we have to do is scale up f of x by 1.3, and this is what it looks like. And this is kind of the thing that we end up with, is that values below the normal distribution line get accepted, values above it that were generated by g of x, those get rejected, but we end up with a normal distribution. So it looks like we can do something similar. I've used 1.5 instead of 1.3, and this is where we are. And it looks like it's going to work for all of these values, but if you zoom in here, what happens is that blue line ends up crossing below the red line, okay? And what we need is the blue line to remain above the red line, okay? So m times g of x ends up being below f of x, okay? So that's with m equal to 1.5. So we can say, well, why don't we just make m bigger, okay? So I could try m equal to 2, okay? And so we could see with m equal to 2, the blue line gets even taller. And so the red line, so f of x actually, if we look at this and this, it looks like the red f of x gets shorter, but it's not. What's happening is that the vertical scale is changing. The vertical scale is changing, and so f of x just gets taller. And so in comparison, the red f of x looks like it's getting shorter, but we haven't actually modified f of x at all. We're just changing our m to be something larger. So the blue line keeps getting taller. And so here m is 2, but if I zoom in here, again, it still crosses f of x, and m times g of x still end up crossing each other. And m times g of x ends up being lower than f of x. And so that's going to be a problem, okay? And I can say, okay, well, let's just try pushing it even higher, okay? So if I set m equal to 6, okay, we could see m times g of x gets even taller, okay? So it seems like, okay, well, that works. And if I look at m equal to 6, the lines don't cross until we get out to, say, around 8.5, okay? Around 8.5. So we get more, okay? So at m equal to 2, it crosses around 6.4. at m equal to 1.5, it's crossing at around 5.5. And so as I push m to be larger values, it doesn't cross until further out. And we can try even like m equal to 60. If I say m is equal to 60, this blue line is super tall. The f of x in comparison looks almost flat in comparison to it. It's not, but in comparison to m times g of x, it looks almost flat. And in this case, the lines don't cross until x is greater than 12, okay? But at around 12.2, 12.27, they do end up crossing each other, okay? Where m times g of x still ends up lower than f of x. And that's because f of x is what we call a heavy-tailed distribution. All right, now you could argue and you could say, well, you know what? If I pick m equal to 60, then the algorithm will work where this statement is true, where m times g of x is greater than or equal to f of x. The algorithm will work and will produce values accurately here, okay? And it's true, it will, okay? And when m is equal to 60, m times g of x is greater than f of x, as long as x is less than 12.275, okay? So if you look at this, it doesn't cross until around 12.275, and so this is going to work for m times g of x is greater than f of x, okay? But what we also see is that this is very inefficient, okay? Hang on a second, my dog needs something from me. Okay, so if you look at this though, how many values are we going to reject? We're going to be rejecting a ton of values, because if you compare this to here, right, what happens is we sample from the blue distribution. This is what we did for the folded normal. We sampled from the exponential distribution. Values that ended up below the red line we accepted, values that ended up greater than the red line, so between the blue line and the red line. So this area up here gets rejected and this area over here gets rejected, okay? And only values below the red line get accepted. And so if you look at this, you know, the vast majority of what's under the blue line is going to get rejected, okay? Only a small fraction that ends up being below the red line are going to get accepted, okay? And so what ends up happening is that in this case, if you have m equal to 60, you're going to get this very inefficient system where you're going to end up only accepting around 1 in 60 proposed values. Okay, so m is 60, we're only going to end up accepting around 1 in 60, so you know, less than 2%. So so if you look at this, so here's just kind of the script that you would run. M is 60, f of x is 2 times, because it's the folded t distribution, so I'm taking the t density with 3 degrees of freedom. I'm folding it in half, so it's going to be twice as tall. So f of x is that. G of x is the exponential distribution. I'm going to propose values using random exponential. I'm going to propose 100,000 of these values. And then whether we accept a value or not depends on you. So that's going to be 100,000 random uniform values. And then my acceptance ratio is going to be f divided by m times g of x. Okay, and so this becomes a logical vector, true falses, depending on whether u is greater than or less than r. And then the proposed of the proposed values, we're going to just keep the ones where accepted is true. Okay, so accepted x is proposed subset of x accepted. And then if we look at how many values we've kept, the length of our accepted x divided by the length of the proposed x, we've only accepted 1.6%, okay? We proposed 100,000 values. We proposed 100,000 values. We accepted only 1,600, okay? So that does not seem like an efficient system, right? It, you know, it's like you make 100 suggestions, like where do you want to eat? and you suggest 100 places, and then you have to suggest 100 places, and you only accept one of those places, right? This is not going to be an efficient system. Okay, so only around 1 in 60 get accepted. So this is not an efficient system, and so what are we going to do? Okay, but if you explore it, it does look like the t distribution. Okay, so to make it, so remember, we're getting values from the folded t, only the positive half. So to make it into the regular t distribution, you can just assign a positive or negative sign at random. So half of the values should become negative. So I'm just going to sample either 1 or -1 with probability 0.5, okay, with replacement. And then I'm going to multiply the accepted values of x and multiply by the sign. So either they're going to get multiplied by 1 or -1. And this will end up being my random t distribution. And here it is, 1,600 values of the random t distribution looks like this. If I run it through the KS test, it says your p-value is 0.67, which seems to pass the KS test. There's no reason to doubt that it came from the t distribution with 3 degrees of freedom. So, so this seems to be okay. All right. And so just a few comments. So it does work, okay? It seems like the values do look like they come from the t distribution, okay? So that's a pro. But arguments against, the cons, it's very inefficient. We're accepting only around 1.6% of the proposed values. And then, and it also doesn't work when x is greater than 12.275. So for values in the extreme tail, which the t distribution with 3 degrees of freedom does produce, not super frequently, but it does produce values that are extremely large. This distribution is not going to work. Okay, so our algorithm, our rejection sampling algorithm, is not going to produce enough values in the extreme tail. So there are better solutions that do exist. There is like a modification of the Box-Mueller transform, but yeah, this rejection sampling runs into some problems. Okay, are there any questions so far, or is this okay? So far so good. Okay, let me go ahead and give you your first view quiz answer. First view quiz answer today is D. D as in dog. D as in dog is your first quiz answer. Oops. All right, and so so for the t distribution, enough work has been done where we have found like an elegant solution. But there's a lot of other situations where such a transformation or such a nice solution doesn't exist. And in a lot of these cases, rejection sampling can end up being very, very inefficient. So, this was just a simple example where rejection sampling is inefficient. But, in other distributions where you end up, especially high dimensional ones, so like something that exists in like 17 dimensions or 50 dimensions or something like that, these kind of methods where you try to generate samples can end up being very inefficient. And so we're going to take a look at Markov chain Monte Carlo, okay, or MCMC. And these can produce the values that you need, okay? And so the key difference here is that with Markov chain Monte Carlo, you end up creating correlated samples, okay, where the next value depends on your current value. But the resulting values that you get do come from some kind of desired target distribution. Okay, so you're going to get correlated samples that fit a desired distribution. All right, so let me go ahead and introduce some basics of Markov chains. So we're not going to get into Markov chain Monte Carlo yet, not today. Today we're going to just kind of introduce basics of Markov chains. Wednesday we'll probably go over properties of Markov chains, and then yeah, maybe by Friday, I don't know. We'll see. We'll see when we get to actually do the Monte Carlo, Markov chain Monte Carlo, the MCMC part, okay? All right. So a Markov chain, and we're going to look at discrete time Markov chains, okay? There's continuous time Markov chains and discrete time Markov chains. And I don't know if any of you plan on going to grad school, but if you go to grad school, you probably take a class on stochastic processes. This is kind of like your very, very basic intro to this concept, okay? And so a discrete time Markov chain is a stochastic process that satisfies the Markov property. Okay, so when we say discrete time, basically it means time is kind of in these segments. So you can think of like turns on a board game, okay? Each turn is like a time, okay? Or you can think of time as like today, tomorrow, the next day, or this year and next year. They are kind of discrete. They're happening at kind of discrete intervals or discrete steps, versus continuous time, which is, you know, a different kind of stochastic process where things can kind of happen, you know, right now. It can happen in 2 minutes. It can happen in 7 minutes. It can happen, you know, in 7.5 minutes or something like that, right? It's continuous. Okay, so anyway, because we're doing discrete time, when you look at your random variables, we would say x at time t, x sub t, x at time t, where t is equal to 1, 2, 3, or, you know, at some countable time, okay? And a stochastic process, basically, it just means you're going to get a sequence of things, and those sequences are random, okay? So stochastic is like another way of saying like randomly determined. So you can think of this as a randomly determined process, which is going to be a sequence of random variables, right? You get a sequence of values, but those values are random. And in this case, for a Markov chain, they satisfy the Markov property. Have you guys heard of the Markov property though? No? Yes? Maybe? Okay. So, so the Markov property is basically saying that, you know, if you got the sequence x0, x1, x at time 2, x at time whatever, going up to x at time n, and the next value x at time n plus 1, what we're saying is that the probability for what happens at x at time n plus 1, okay, what's the probability x at time n plus 1 equals some value j? The probability of x at time n plus 1, okay, technically, right, like what's going to happen tomorrow in your life, if you think about it, where you are today and what's going to happen tomorrow in your life, like, is like the culmination of everything that has happened in your past, right? Like, who were your, what happened in your childhood, and who were your parents and your siblings, and what happened to you in 2nd grade and 3rd grade, and did your teacher in 9th grade like you, and things like that. And then, you know, all of that shapes you. And so, you know, you know, how are you feeling about what's going to happen tomorrow? Like, that depends on like so much stuff in the past, right? So you can think of that as this, and so it's really like this huge conditional probability of all of this stuff that has happened in your life, okay? But the Markov property, and this is some people's, this is their philosophy in living life, and whether you agree with this or not, and it's that what happens in the next step, x at time n plus 1, depends only on what happens at time n, okay? So everything that happened from here all the way up to here, everything that happened before today, it doesn't matter, okay? That's the Markov property, is kind of this idea that it's memoryless. What happened in the past doesn't matter. The only thing that's going to determine tomorrow is where you are today, okay? Is that x at time n what happens at x at time n plus 1 depends only on x at time n, okay? Everything that happened from 0 to n minus 1, all right, from day 0 to yesterday, that doesn't matter. It only just matters where you are today, x at time n, and that's what's going to determine at x at time n plus 1, okay? Now, I don't know if humans can live this way because we have memories and trauma and stuff, but this is kind of the idea, and so it's like a simplified view of how things could work, okay? And so so that's what the Markov property is. This is the Markov property stated mathematically, okay? But it just basically means what happens in the next step only matters on where you are right now, okay? The current state. The state space of a Markov chain is going to be all the possible values that these values can take on, okay? X at time 0, x at time 1, what kind of values can we end up with, okay? And that's going to be the state space. So maybe it's all the numbers, maybe it's only some values. That's that. Okay, so the Markov property means that the probability that the chain moves to state J on the next step only depends on the current state, not on where the chain has been previously. Okay, so that's kind of, I think, what I said. That, you know, the next step only depends on the current step or current state, nothing that has happened before. All right, and so we're only going to consider, you know, as far as this class goes, or right now, we're going to look only at Markov chains with countable or finite state spaces. Okay, so discrete. So this means we've got discrete state, discrete time Markov chains, and this is, again, if you take a class on stochastic processes, you can have continuous state, continuous time, you know, all sorts of stuff, okay? But we're going to look at discrete state. All right, so that means our state space is going to be countable or finite, okay? So if it ends at some value big N, then it's finite, or it could also just go off to infinity, but it's still countable, right? Versus, you know, uncountably infinite. All right. I don't know what, I'm not sure what's wrong with my dog. I thought I took care of what he needed. Okay, so we can create a set of transition probabilities, okay? Transition probabilities are going to be defined as the conditional probability, which says that, you know, what is the probability that at the next time, x at time n plus 1, what is the probability that at the next time you're going to end up at state J? Given that right now at time n, you are at state I, okay? So it's basically, what is the probability of going from I, state I right now, to state J in the next step, okay? So that's what this is. P sub ij is the probability of going from I to J. If you are currently at state I, what's the probability you end up at J? Okay, that's P sub ij. That's the probability of going from state I, given that you're currently at time n, you're at I, that you will end up at state J, okay? So you can think of this, if you think of literal states, like states in in our country, the United States, you could think of this as like, right now you are in California, and this year you are in California, and what is the probability that next year at time n plus 1, you end up in a different state? So what is the probability you end up in Texas next year or something like that, okay? So that would be the probability of starting in California and ending up in Texas the following year, okay? And, or you can say, well, you know, or you can have probability of starting in California this year and ending up in California next year. Or you could say, you know, what's the probability I start in California and move to New York or something like that, okay? Or, you know, so if we do this for all 50 states, how many transition probabilities total exist? What do you guys think? So if we're limiting ourselves just to the United States, so we've got 50 states in in the US, right? So we're going to end up with a big 50 by 50 matrix, okay? We're going to end up with a 50 by 50 matrix representing where you are now. So you'll have 50 rows to represent where you are now. And then you'll have 50 columns for where you could end up next year, okay? So you'll have a row for California. And if you start off in California, technically, next year you could end up in any of the other 50 states, okay? Probably the largest value is going to be starting in California and staying in California next year, okay? But there's going to be a transition probability of starting in California and ending up in Alabama, or starting in California and ending up in the next state, Alaska or Arizona, Arkansas, you know, California, Colorado, Connecticut. I don't know if you guys, well, anyway. So you start off in, so you're gonna have 50 states to kind of, 50 rows to stay where you are currently, and then 50 columns to where you end up next year, okay? And so you'd end up with a 50 by 50 matrix, all right? And so, and it would all represent from starting in state I and ending up in state J, okay? And that, I mean, that's like a literal states thing, but, you know, it could be something else. And so we can represent all of our transition probabilities with a big transition matrix, okay? So if we say this first row, if we go alphabetical order, this first one would be Alabama, okay? So we could say this would be the probability of starting in Alabama and ending up in Alabama next year, okay? And then this, if we go alphabetical, this would be starting in Alabama and ending up in Alaska, okay? I don't imagine there's a high probability that somebody starts off in Alabama and ends up in Alaska, but, you know, the probability is not zero, okay? It's pretty low, but not zero, right? And then Alabama to Arizona, wait, Alabama, Alaska, yeah, Arizona, okay? And then the next would be Arkansas, and so on and so forth, okay? So I imagine if you currently live in Alabama, then the highest probabilities will be basically the diagonal, that people will just stay put, right? If you're currently in Alaska, next year, you're most likely to still be in Alaska, okay? If you're currently in Alabama next year, you're most likely to end up in Alabama. But Alabama probably will have slightly higher transition probabilities to adjacent states like Mississippi and Georgia and Florida. I don't know what borders Alabama, okay? So I imagine the adjacent states will have slightly higher probabilities, and then probably large population centers like California, Texas, and New York would have higher probabilities. But probably, you know, very low probabilities will be people going from Alabama to Alaska, Alabama to Wyoming, or something like that. I imagine those being fairly low transition probabilities and stuff like that, okay? And then this next row would be people who currently live in Alaska and then move to start off in Alaska and then end up in Alabama, start off in Alaska, end up in Alaska. This one would probably be the highest, and then Alaska to Arizona and things like that, okay? So anyway, we're gonna end up with like 50 by 50 or however many states that are available in rows and how many states are available in columns. And so the rules are what? The transition probabilities are non-negative. They're also technically bounded by 1 as well, okay? I guess that's going to become obvious here, is that the sum of the rows, if you look at each row, the sum has to add up to 1, right? Because this top row is where you're going to end up if you are currently in Alabama. You have to end up somewhere. You have to end up somewhere next year, okay? And you're either going to, and so if you add up all of those locations of where you end up next year, they have to add up to 1, okay? And so if you sum across all of the columns for a particular row, they're going to add up, it's going to add up to 1. Okay, current state I is the row, and the next state J is the column. So that's the transition matrix. Okay, so here is a very basic diagram. Forgive my illustration here. And this would be a 2-state diagram with 2 possible states. So you can think of this, I don't know, a possible example is A could represent sunny weather and B could represent not sunny weather, okay? And so from A, you could end up going back to A. So if it's sunny today, you could end up being sunny tomorrow, okay? Or if it's sunny today, it could end up being not sunny. It could end up being cloudy or rainy or something different tomorrow, okay? And then if you're currently having cloudy or not sunny weather right now, you could end up back having cloudy or rainy weather tomorrow, not sunny. Or it could transition from cloudy to sunny, okay? So with two possible states, there are a total of 4 transitions. You can go from A to A to B, and from B, you can end up going from B to A and B to B. So you have a 2x2 matrix to represent your 4 possible transitions when you have a total of 2 states. So we can add the the probabilities or to the transition matrix to the state diagram. So here is the transition matrix. So this is 0.7. So if you label these, this top row is for currently in state A, and the second row is currently in state B. And then this first column is moving or transitioning to state A or transitioning to state A for this first column. And then the second one would be transitioning to state B. So this one, 0.7, represents starting in state A and ending up back in state A. So this is my, this arrow gets labeled 0.7. This 0.3 is starting in state A and transitioning to state B. The 0.4 is starting in state B and transitioning to state A. And then 0.6 is starting in state B and ending up back in state B next at the next time. Okay, so what we're saying is that if it's sunny today, there's a 70% probability that it'll be sunny tomorrow, and a 30% probability that it won't be sunny, state B. Okay, and if it's not sunny today, which is state B right now, there's a 40% probability it'll be sunny tomorrow, and there's a 60% probability that it won't be, that it'll still be state B tomorrow. Okay. Again, the rows must add up to 1. The probabilities in each row must add to 1. And then if you look at the arrows that originate from a single node, okay, those have to add up to 1. Okay, so the arrows originating from A have to add up to 1. The arrows originating from B have to add up to 1. There's no rule that says the arrows entering a node have to add up to 1. Okay, so going to B, we got 0.6 and 0.3. Those don't have to add up to 1. Going to A, 0.7 and 0.4, those don't have to add up to 1. But those coming out of A have to add up to 1, and those coming out of B have to add up to 1. And likewise, the rows have to add up to 1. All right, is this okay? All right, let me give you your next quiz answer. Next quiz answer is C as in California, or C as in cat. C. Okay, all right, I gotta go a little bit quickly. All right, so here we can have a Markov chain representing the Ehrenfest-Ern model, okay? And this can be used to kind of model the diffusion of molecules through a membrane. And what we're gonna have is we've got 2 urns labeled A and B, and there's a total of n balls in these 2 urns, a total, okay? And at each step, a ball is randomly chosen from all of the n balls total and moved from one to the other urn, okay? So either we pick a ball in urn A and move it to B, or we pick a ball in urn B and move it to A, okay? And so x sub n is going to be the number of balls in urn A at step n. And so the possible values for xn are going to be 0 through big N. We've got a total of big N balls. So you can have anywhere from 0 to big N in urn A. And the sequence, x sub 0, x sub 1, x sub 2, all the way up through x sub time n, is going to be a Markov chain where the possible values are 0, 1, 2, all the way up to big N. Okay, so if there's currently I balls in urn A at step n, that is to say x at time n is equal to I. So if there's currently like 2 balls in urn A, Then at the next step, either we take one of those balls and move it out and we end up with one ball in urn A, or we take a ball from urn B and move it to urn A and we end up with 3. So if you currently have 2, in the next step, you're either going to go down to 1 ball or you're going to end up with 3 balls, okay? So at the next step, if you currently have I, you're either going to end up with I minus 1 or I plus 1. And those are really the only 2 possibilities, okay? You can't, because there's always at every step we're moving one ball from one side to the other or this side to this side, you're not going to stay stagnant, okay? So you can't end up with I, and you can't end up with more than I plus 1, or you can't end up with less than I minus 1, okay? So if you currently have I right now at step n plus 1, you're either going to end up with I minus 1, or at step n plus 1, you're going to end up with I plus 1, okay? And then there's a total of n balls total, and every ball, each ball has the same probability of being selected. So the probability that a ball is chosen from a particular urn, whether it's from urn A or urn B, is going to be proportional to the number of balls, or is going to be the proportion of balls that are in that urn. Okay, so I've illustrated this with a set with n equal to 4. Okay, so we have a total of 4 balls, and right now I've got 2 in A and 2 in B. So x at time n, x sub n is equal to 2. We've got 2 balls in urn A. All right, and so these are the 4 possibilities, right? We're going to select 1 ball at random. Okay, so here I can select this one, or I could select this one, or this one, or this one, right? So there's 4 possible balls that I can select, and I've listed them off. And so if I select this one, I'm going to end up with 1 ball in A and 3 in B. If I select this one, I end up with 1 ball in A. If I select this one, I end up with 3 balls in A. And if I select this one, I also end up with 3 balls in A. Okay. And so if we look at the 4 possible, out of the 4 possible states that we end up with, 2 of them have 1 ball in A, and 2 of them have 3 balls in A, okay? So the probability of starting off with 2, probability of going from 2 to 1, which is what we have, is 0.5. And the probability of starting at 2 and ending up with 3 is also 0.5. Is that all right? Okay. And then similarly, here's just like a different configuration, okay? If I start off with 3 balls in A, then we could see what happens, right? So I could pick this one, this one, this one, or this one. I could pick one of those 4 balls, okay? And if we look at that, out of 3 of those, okay, I go from 3 balls down to 2 balls, okay? Because if I pick this one, I end up with 2 balls. If I pick this one, I end up with 2 balls in A. And if I pick this one, I end up with 2 balls in A, okay? But if I pick this one, I will end up with all 4 balls in A. So the probability of going from starting with 3 balls and ending up with 2 balls, so the probability of going from 3 to 2 is 3/4 or 0.75. And the probability of going from 3 to 4, starting off with 3 balls and ending up with 4 balls, is going to be 0.25. Okay, so it could happen, but it's not equal probability. Right? And so you can kind of apply this logic and apply this to the full transition matrix, right? So we figured out the probabilities for basically these two rows here, going from 2 balls to 1 ball, 2 balls to 3 balls, or 3 balls to 2 balls, and 3 balls to 4 balls. I've drawn these ones out, but you can kind of think through the logic, and you'll see that the other transition probabilities are going to be this. Okay, and so more generally, the transition probabilities, so you can take all of the transition probabilities in this matrix and put it into the state diagram. And we can go from 2 and we'll move to 3 with probability 1/2, or we can start at 2 and move to state 1 with probability 1/2. If we start off with 3, we go to 4 with probability 1/4, or if we start off at 3, we end up with 2 with probability 3/4. Okay, and so on. And you can apply this to the entire matrix, which is what we have here. And so more generally, if you kind of expand this to a total of n balls, okay, the probability of, if you start off with I, the probability that you end up with I minus 1 is going to be, you have to pick one of your I balls. And so you got, that probability is I over n. And then if you start off with I, the probability of ending up at I plus 1 is going to be 1 minus I over n. Okay. And then so when you fill out the matrix, the probability of starting off at I and ending up at j is going to equal this, you know, when j is equal to I minus 1 or when j is equal to I plus 1. And it's going to be 0 everywhere else. So that's the earn model here. All right. Okay. And then we'll do the random walk, and I can go through this quickly. Let me give you your last quiz answer. Last quiz answer is A as an apple. A as an apple. Last quiz answer today. All right. So the random walk, again, another discrete time stochastic process. We can use it to model the path of an object or particle through space. Brownian motion, which I think was Einstein's first, one of his first papers was on Brownian motion. That's like a particle through liquid or gas. That can be treated as a random walk. We can think of the path like an insect takes as a random walk. Gamblers' winnings or losses or stock prices. These can be treated as random walks. And so we're going to just look at one-dimensional random walks. So for a one-dimensional random walk, basically we're going to say you can either move to the right or go up one, or you can move to the left or go down one. Okay. We're going to start off all of the Markov chains at 0. And so, you know, the sequence of values up through time n is going to end up being all of the integers, because you're either going to go +1 or -1. Okay. And we're going to say you go +1 with probability p, or you move left -1 with probability q, which is equal to 1 minus p. Okay, so p and q add up to 1. So go to the right with probability p, go to the left with probability 1 minus p. Okay, so if you start off at 0, then at time 1, you will either end up at 1 or -1. 1 with probability p and -1 with probability q. At any state n, at time n, if you're currently at state I, you're either going to be at I +1 with probability p, or you're going to end up with I -1 with probability q. And you can thus define your transition probabilities. And so for I, you're either going to end up at j, which is I +1 or I -1, and that's going to happen with probability p or q, and so on. So kind of similar to the earn model, okay, except this is unbounded. Okay, the earn model, we were bounded to big N, how many balls total, and here we are unbounded. And the probability of transitioning left or right remains constant, PQ, which wasn't the case with the earn model. All right, and so, and we can also express this as a sum of IID variables, right? So we can say, you know, let y just be either 1 or -1, and it's 1 with probability p, or it's -1 with probability q. And we can also just treat the sum of the x as the sum of, you know, the previous value plus the next value y of 1 or -1. I know I'm going through these quickly, but I think you can also read through and review these, and it will make sense. Okay, so anyway, here's just coding up a random walk. I've got, we're going to look at 1,000 iterations. P is 0.5, Q is 1 minus 0.5, also 0.5. Okay, and then I'm going to just generate random values of y, which are either going to be 1 or -1. And we're going to sample these with replace equal to true. Here it doesn't matter because P and Q are both 0.5, but you know, you could set different values for P and Q, and it would have different probabilities. And then my random walk of x could just be treated as the cumulative sum of y, you know, starting off at 0. Okay, so here's one random walk. I start off at 0 and I go up, left, right, up or down, and here I end up with at -40 after 1,000 iterations. Here's another random walk. Okay, I start off at 0 and I go up and down, and here I go up some and down some, and I end up around +40 after 1,000 iterations. Okay, that's just a coincidence. And see, I think we can see how, you know, we could treat stock prices or random walk, earnings and losses, kind of like a random walk. So so anyway, these are just a few examples of Markov chains, and so on Wednesday we'll continue this and look at this some more. Okay, that's all I've got for you guys today. Sorry for going a couple minutes over, but we'll end here, and we will see you guys on Wednesday. All right.